Okay, so hello everybody. Thanks for getting back to us here. So it's for our third talk of today. It's a great pleasure to have Giulia Sacca, who will speak on fixed loci of anti-symplectic involutions. And I checked that on the Cambridge Dictionary. The pronunciation in U.S. English is loci. Anyway, but feel free to pronounce it however you want, of course.
Loci, as opposed to.
I've heard people saying loci.
Oh, I would have said loci, but I mean, I don't know. I'm not a native speaker. I mean, it's a Latin word, but.
Anyway, okay, so sorry for that little comment. But anyway, so yeah. So Giulia, thank you.
All right. Well, thank you very much for the invitation. It's been a very interesting workshop. I feel maybe I'm not as sort of in. Anyways, my talk will have some Hodge theory, but maybe it's not like in the sort of, I see a lot of people, more giving talks more in sort of works that they're doing together and stuff, but hopefully it will be of interest. Okay, so this will be, this is joint work with Laura Flapan, Emanuele Macrì, and Grady. It appeared this morning on the archive. I guess part 1 and part 2 will follow hopefully shortly. I'll tell you what is on the current paper and what is still to be written. So in this talk, X will denote hyperkahler manifold. And by hyperkahler manifold, this means, in fact, irreducible holomorphic symplectic manifold, which means that it's simply connected, compact kahler, simply connected, and holomorphic 2 forms, one-dimensional and spanned by a holomorphic symplectic form. Okay, and so the sort of trivial example is K3s. And in higher dimension, and these are mostly example we'll be concerned with, 2n, we have Hilbert schemes of points. And their deformations, and their deformation include moduli spaces of sheaves or objects in the derived category of S. And if I fix the invariance in the algebraic cohomology group of S, and I denote such moduli spaces like this, and they are also, for sufficiently good choices of V and stability condition, they're hyperkahler manifolds, and their deformation to these Hilbert schemes, deformation equivalent to the Hilbert schemes, and so these things are all deformation, and this deformation class is called K3n type. And just because of what I'm going to need later, let me just remind you that for K3 surface, the deformation space is 20-dimensional, and inside that we have countably many hypersurfaces that correspond to the Noether-Lefschetz loci, and which parameterize S, H, where H is a algebraic class, a line bundle, and so in particular, for example, S may be ample, and so these are polarized families. If this is for K3s, and for K3n type, the moduli spaces now are 21-dimensional, and the projective hyperkahler manifolds that you get, these are projective. So the projective families that you get from K3 surface correspond to codimension 2 loci inside the full deformation. Of course, if you take all the Hilbert or Duodec spaces, that's a codimension 1 family inside that thing. But if you're interested in projective hyperkahler manifolds, these are codimension 2. And sort of one of the things is how to construct polarized families of codimension 1, and sort of this relation with Fano varieties answers one of these questions. Okay, so there are other deformation classes. I won't enter I won't say anything about them. not today at least. Okay, so the important tool is the Boville-Bogomolov-Fujiki quadratic form. And so the integral cohomology of a hypercal manifold has a quadratic form of signature 3, second Betti number -3, which is compatible with a Hodge structure. And the weight to Hodge structure, let me remind you that the important feature here is that the first non-zero Hodge numbers are one-dimensional because of the definition here. And so in particular, if sigma is the symplectic form, it's isotropic with respect to the quadratic form, and sigma sigma bar is positive. Okay, and so let me maybe give you the example just to fix maybe what's going on here. For a Hilbert scheme of points on the K3, then this is trivially, you can see that, well, the H2 is the direct sum of the H2 of the K3 plus delta, which is 1/2 of the locus of non-reduced points, the exceptional divisor of the Hilbert Automorphism. And so the Boville quadratic form restricts to just the intersection product here, and this is orthogonal, and delta squared is equal -2 and -1. Okay, so how do we use this? We use this in the period mapping. And so the deformation space is smooth of the expected dimension, which is equal to H11. And sort of if we fix a marking, meaning an isomorphism between the cohomology, second cohomology with a fixed lattice, we have the local period mapping with values in projectivization of this, and in fact it lies into this the period domain, or one component we can choose. And sort of this is a local isomorphism. And of course, since we're going to be concerned with polarized families, if we choose a class here correspond to an ample line bundle, then it's the square is positive. And then here the periods of the deformations of X together with H lie in the intersection of the period domain with the sort of H perp with the orthogonal complement. Okay, so this is a type 4 period domain. It's sort of very nicely behaved, and sort of that's where you get sort of, and the periods correspond to periods of polarized hypercal manifolds with this with the deformations of this line bundle. Okay, and I'm just setting a little bit of background and notation. So now that we have the period, the local period mapping is an isomorphism, the local isomorphism, that's what is usually called local Torelli. You can ask, what about the global Torelli? And the answer is no in general, because a result of Huybrechts says that if f, x, and x prime are birational, and then they correspond to non-separated points of the moduli space. And here I should say which moduli space of mark pairs. But I don't want to give too many details, but the point is just that they can, the birational map can be obtained as a limit of isomorphisms. Okay, and so in particular, because this is gives a canonical identification with between the second cohomology groups, then you can see that this gives counterexample to global Torelli. And so in fact, this is basically the only thing that can go wrong on each connected component of the moduli space of marked pairs, this is the only thing that go wrong. Two things have the same, this is the only obstruction to injectivity, to global injectivity. If two marked pairs have the same period, then they correspond to birational things. And I should say that it's also known that the period map on the global moduli space is surjective. Okay, so we see that here the issue is about birational morphisms, and how do you get rid of this? Well, this is one of the reasons why considering instead of just marked hyperkalers, but marked polarized hyperkalers, because if a birational map sends a Kähler class to a Kähler class, or an ample class to an ample class, well, Kähler class to a Kähler class, then it's Fn is an isomorphism. So when restricting to polarized hypercal manifolds, in fact, the global Torelli theorem holds in the way that you expect it to. And so let me maybe give you the precise statement. And so here's the polarized Torelli theorem. So let phi from H2 of xc to H2 of x prime z, so x and x prime hypercal manifolds, be a parallel transport operator. I'll say what I mean in a second. Which is an isomorphism of integral Hodge structures. Okay, and so let me finish the statement and then I'll say what a parallel transport operator is. Then there exists isomorphism from x to x prime such that f lower star is equal to phi if and only if phi maps a Kähler class to a Kähler class. Okay, and so here I set the name Verbitsky. I should also add so Verbitsky. I should also add Markman and Hoybrechts. Okay.
Can I ask you a quick question?
Yeah.
Is this for any hyperkahler, or is it just for the ones that have the form K3 symmetric?
This is for any. So what changes up on the deformation class are two things. This group, I'm going to say what it is in a second, and then also the kernel from the automorphism group of X, or maybe birational automorphisms, into the automorphism of the second cohomology group. So here I didn't write unique, right? Which, for example, for K3 holds. And so whether or not that is unique depends on the deformation class. For those guys above, then it is unique. But for example, for a generalized comer, it's not unique. There's a kernel here. Does that answer your question?
Yeah, thanks.
Okay, and so parallel transport operators, I just mean isomorphism in cohomology given by parallel transport along a continuous loop, continuous path on a smooth family, on the base of the smooth family. Okay. And so what does change from, depending on the deformation class, is what this group is. So when I look at parallel transport operators that operate from the H2 of X to the H2 of X itself, this is what is called the monodromy group, which is inside H2 of XZ. And so what this group is depends on the deformation class, and it's in general a highly non-trivial result to compute it. And so for K3n, this was computed by Markman. Okay, and so if you know that your lattice automorphism is a parallel transport operator, then you know that it lifts to an automorphism. Okay. And so then the question of, so then such a statement, of course, gives sort of, first of all, you need to study the monodromy group. And then, of course, you want to reduce geometric statements to lattice theoretic statements. So, and the same thing you do with K3s and how you study automorphism with K3s, then you look at automorphism of the lattice, and this is a similar thing where instead you get both regular isomorphisms but also birational maps. I haven't, there's a version of this for birational maps instead of isomorphisms, but I'm not gonna like say anything. And so then at the same time, so you also want to sometimes go in the opposite direction, is how to find geometric interpretations of lattice theoretic statements. And so let me give you an example of what I mean by this. And this is kind of some of the one part of the motivation of the work that we've been doing. So one example is finding locally explicit geometric descriptions of locally complete projective families. So codimension 1 families of polarized hypercal manifolds. The existence of such families follow from the surjectivity of the Torelli map together with lattice statements about which squares of ample line bundles occur and so on and so forth. But how to find them geometric explicitly, that's another question. And so another example of this is that you get often unexpected isomorphisms between moduli spaces of lattice polarized or polarized. Maybe let me just say lattice polarized. It includes the polarized, lattice polarized hypercal manifolds. And here I should maybe write the bar and okay, and so let me just give you an example. It's going to be relevant for later. For example, if you look at hypercal manifolds of K32 type, together with ample class of squared 2n minus 2, the moduli space of these, I'm kind of hiding some other conditions that I need on H, but let me just be a little vague. The moduli space of this corresponds to the moduli space of K3n type hypercal manifolds with a polarization of squared 2. And so the statement is just a lattice theoretic statement about what is the period domain corresponding to these things. And so then the question is there a geometric interpretation? Okay, and so in terms of answering the first kind of question, a big source comes from Fano varieties. So This comes from Fano. Maybe I should say hyperkalers constructed from Fanos. Okay, and so let me remind you some example of this and why they give you sort of full families of polarized hypercal manifolds, differently from what we saw earlier for K3, where you only got codimension 2. Okay, and so the first example is cubic fourfold. So smooth cubic fourfold. And there's several ways to attach to the smooth cubic fourfold a hypercal manifold. And the first is the Boville-Donaghy. So this is f of y. It's the Fano varieties of lines in y inside G 2, 6. And this is, if y is smooth, this is a hyperkahler fourfold of K32 type. And also the Plucher line bundle is sort of is a natural ample line bundle on this thing. Generically, it's the only ample thing, only is a generator of the Picard group, and it has square 2. And in fact, since cubic fourfolds deform in a 20-dimensional family, these things here, Fy, give the general element of polarized K32 type with a class of square 2. And so they're like the general point in the hypersurface. Okay, so that's the first example. And the second example is, sorry, that was not a Roman 2, but okay. So the second example is the Len, Sorga, Van Straten eightfold, and I'll denote it by Z of Y. And this time, instead of parametrizing lines, rational curves of degree 1, we parameterize rational curves of degree 3, so twisted qubits. And in fact, we want to put an equivalence relation on the twisted cubics because we want to identify if I have a twisted cubic here on NY, its linear span is a B3, and generically it will intersect the cubic in cubic fourfold in a cubic surface. And so the whole two-dimensional linear system of twisted cubics on that same cubic surface is all identified under this equivalence relation. And basically, that's almost the only thing that you identify. I don't want to say more. But if you didn't do this, this would have this would be a P1 bundle, and there's no chance you'd have a symplectic form on it. Okay, so this also comes with a natural polarization because there's a natural map. It's only rational, but to the Grassmannian of P3s. So to a curve here, an equivalence class, you associate the P3 in the Grassmannian. And the pullback gives also, okay, sorry, here, it's not 2, but it's 6, sorry. Apologize. Here, now the pullback of this of the Plucher line bundle now is actually square 2. Lambda square equal to 2. Okay, and so let me zoom out a second, and of course, so again, these form this locally complete family of polarized hyperkahler manifolds, and the fact that in both cases the construction comes from the cubic fourfold. The moduli spaces are exactly the moduli space of cubic fourfolds. And so this isomorphism that I had here, in the case where n is equal to 4, gives me the fact that we have this sort of identification of moduli spaces. And so you see that these hyperkalers that you construct from Fanos not only give you a nice complete family of polarized things, but also give you geometric interpretation of these isomorphisms. Okay, so there's another, there's also the intermediate Jacobian fibration. Let me get Jacobian fibration. Not going to say anything, so this is just and work with Grady and Claire, and then also on my own. Now, I don't want to mention this because this is not of K3n type, but this is of a Grady 10 type, which is a different deformation class. And in fact, this is a codimension 2 family. So we're not interested in this from this point of view. What is a convenient way of generalizing both the Boville-Donaghy Fano 4-fold and the Lendland-Sorghum-Stratton 8-fold? Sorry, I didn't say this is hyperkahler 8-fold of K3 4 type. Okay, so a way of generalizing both 1 and 2 is as following. So moduli spaces of bridge and stable objects on the Kuznetsov component of the cubic 4-fold, which is inside the derived category. And here I should write the names of Kuznetsov, of course, and Bayer, Lautz, Macrì, Stellari, Bayer, Lautz, Macrì, Neuer, Perry, and Stellari. And all of these give rise to polarized, maybe let me, to complete family, to locally complete polarized hypercal manifolds of K3n type. And there's also, you can also recover some Grady 10 examples in this way, but I should remark that for Y very general, the intermediate Jacobian fibration is not birational to one of these moduli spaces. Okay, so what's going on here is that the fourth cohomology group of the cubic 4-fold is in fact a weight 2 Hodge structure because the 840 vanished because of the Fano condition, and the first non-zero Hodge numbers are 1, and so this is really what's going on. And in fact, there are many ways. There are other now Fano manifolds that you can associate hypercal manifolds to, and so one is Giulia of even dimension, and de Bar-Voisin varieties. And so these have been successfully used to construct hypercal manifolds. And it turns out they're all K3n type, those constructed this way. But also there's they kind of generalize the Griffith's residue theory to study a cohomology of complete intersections in not only in projective space, but in Grassmannian or other homogeneous varieties to kind of cook up examples of these Fano varieties of K3 type. So Fano varieties of K3 type, by which I mean that there's some cohomology group that is actually like this weight 2 Hodge structure with H20 equals to 1. Okay, so in this talk, we kind of go in a different direction, and we kind of would like to reverse the construction and starting from hypercal manifolds and polarized hypercal manifolds, just find the Fano. So that was one of the motivation, and together with this sort of understanding these unexpected isomorphism between moduli spaces. So I'll try and discuss the work now. Any questions so far? Okay, and I'll keep going. So this is where I start talking about anti-symplectic involutions. So let me start with a few examples, and we're going to try and generalize from these examples. So the first example is on the Len-Len-Sorgen-Straton eightfold. There is a natural anti-symplectic involution. Which I'm going to denote by tau. And anti-symplectic, of course, just means that the action on the symplectic form is minus the identity. And so let me describe you. It has a nice geometric interpretation. It goes as follows. So if I have an equivalence class of twisted cubics, again, I have my P3 generated by the twisted cubic. And for any, this is a P3, and for any quadric surface containing in P3 and containing the curve, the intersection of the smooth surface with the quadric, this is a, right, this was the intersection of this with the cubic fourfold. This is a sextic curve, so it's a union of C and another irreducible component, which is exactly what we sent this, which is also a twisted cubic, and is what we sent this the equivalence class of C prime. Okay, and it does not depend on the quadrant you choose, and it respects the equivalence relation, and so on and so forth. Okay, so there is this natural involution, and let's look at the fixed locus. And it turns out, it requires a proof, but it turns out that this has two connected components. One of which is isomorphic to y itself. So you have this anti-symplectic involution on this eightfold, and the fixed locus, I should say the fixed locus of a Lagrangian, so general fixed locus of anti-symplectic involution on a hypercal manifold is always smooth because it's a fixed locus of finite group action, but it's a Lagrangian submanifold.
Giulia?
Yeah?
Can you repeat what Y is?
Y is a, sorry, okay, here, thank you, that was a Y. And Y is a smooth cubic fourfold. And in fact, in this example, it should not contain a plane. And not containing a P2. Is that clear?
Thank you.
Mm-hmm.
Okay.
Okay. So here, of course, it's very relevant for the talk, just the fact that the fixed locus, every component of the fixed locus is half dimension, and the tangent space is an isotropic subspace of the Lagrangian, of the symplectic form because of this condition. Okay, and the other observation is that the action on this natural line bundle of square root 2, which came from that Plucher from the Grassmannian, is this happen. Okay, and so that was the first example. And maybe before actually saying this, the sort of general picture that we want to generalize is, so you start, maybe before, let me say this. And so the remark, in this case, then you have this fixed locus of the involution here, and you recover both z of y and f of y as moduli spaces of objects in the Kuznetsov component of y. Okay, so this is kind of the general picture that we're aiming at, which most of which will be only conjectural, but we have some sort of first results in this direction that I will mention. Okay, so that was a good example. A different example, I don't know if it's good or bad, but just different, is if you want the sort of the simplest example of a anti-symplectic involution on a hypercal manifold, especially if you want the involution to deform in a codimension 1 family, that's a genus 2K3. So S lambda square is equal to 2. If lambda is ample, there's a 2-to-1 map to P2, and there's an involution which is anti-symplectic because P2 has no holomorphic 2 forms. And of course, the involution preserves this class because the class lambda comes from P2. And but the fixed locus now has a very different nature. It is, first of all, connected, and it is the ramification locus, which is the sextic curve. In particular, it's of general type, so very far from being Fano. Okay, let me give another example, which is more in the spirit of the second example rather than the first. That is the example of double EPW sextates. And so now in P5, we consider a singular sextate hypersurface. I denoted why A depends on some linear algebraic data, which I'm not going to specify, but to distinguish it from the cubic fourfold. So this is a singular sextate hypersurface whose singular locus has codimension 2. It's smooth, and it has codimension 2. And the result of Grady is that there exists a 2-to-1 cover of this, which ramifies exactly on the singular locus. And this 2-to-1 cover is, under some genericity assumption, is a smooth hyperkahler fourfold. And again, if you take the pullback of the O of 1 from downstairs, we call this lambda square is equal to 2. And these form a locally complete family. So codimensional 1 family of polarized. Okay, and this, of course, there is an involution that's realized as a double cover. So there's a natural involution there. And what is the fixed locus? Well, by construction, the fixed locus is the singular locus of the thing downstairs. And this is connected and is of general type. So I don't know if I should write here Ferretti and Welters. And a surface is a surface of general type. Okay, and so let's look at these three examples, and what do these examples have in common? We have an anti-symplectic involution. There is some line bundle that is preserved. It has square 2, but the fixed loci have very different nature. So, so let me maybe state out what happens. What these examples have in common are the following. So you have a complete family of polarized hyperkahler of K3n type, and lambda square is equal to 2. And there exists anti-symplectic involution acting on the hypercal manifold. And if you look at the action on on the second cohomology group, it preserves a line bundle, but preserves lambda. But the fact that it deforms in this codimension 1 family forces the whole complement, the orthogonal complement of lambda, to be acted upon by multiplication by -1. The whole rest is anti-invariant. So what I want to say is that the action here is the reflection about the class lambda. So it acts like x goes to -x plus x lambda lambda. Lambda has square 2, so this is a nice sort of involution, and it turns out that all of these examples have this in common. Okay, so how do you distinguish the first example where you have 2 components and a Fano component from the other 2 examples where there's connected fixed locus and a general type fixed locus? And so the difference is the following. Again, you go to lattice theoretic properties. So what is the difference? So in example 1, the divisibility of the class lambda is equal to 2, and I'm going to say what the divisibility is in a second. And in example 2 and 3, the divisibility of lambda is equal to 1. And so let me remind you that if I have a lattice and an element in the lattice, I can look at the ideal in Z generated by intersecting X with all the elements in the lattice, and the divisibility of X is a positive generator of that ideal. And so in particular, if the class is a square 2, the divisibility has to divide 2, so it's either 1 or 2. Okay, so I think you can probably imagine where this is heading. And so let me give you the general setup. So we start with a polarized manifold of K3n type, where lambda squared is equal to 2. And again, of course, the divisibility has to be equal to either 1 or 2. And the remark is that such a pair exists So in now we have to distinguish the 2 cases. For every n, with if divisibility is equal to 1, and if and only if n is congruent to 0 modulo 4 if the divisibility is 2. And these are lattice theoretic conditions that guarantee the existence of these polarized families. And when these pairs exist, the moduli spaces are irreducible. Okay, and so the sort of Torelli theorem, together with the computation by Markman of what the monodromy group is, implies that if we have such an X with such a lambda, the reflection on about this, the reflection about this square 2 class is a parallel transport operator. And so, because it preserves the class lambda, which I'm assuming is ample because I'm in a polarized case, then there exists automorphism of X corresponding to that action on cohomology. And because it acts on as -1 on the complement of lambda, it has to be an anti-symplectic involution. Okay, so let me then give you the theorem. So let X lambda be as above, with tau acting on X, the anti-symplectic involution. So first is that the number of connected components of the fixed locus of tau inside X is exactly equal to the divisibility. And 2, in the divisibility 2 case, then there exists one component. Sorry, how do I want to say this? One component is a Fano manifold. Then one component is a Fano manifold, Fano n-fold of index 3. And more precisely, the canonical bundle of this Fano manifold is equal to -3 times lambda restricted to F. Okay, so this is the sort of the paper that came out today on the archive. Unfortunately, just has the first part, and the first part is hopefully it will be up soon. It's kind of half written, but we're gonna sort of add a few things, so we haven't posted it yet. And so I part of what this what these works what we're doing with my collaborators, we're sort of setting up this ways of studying these anti-symplectic involutions, and we're gonna I'm going to tell you a little bit what the sort of main inputs are in the remaining part of the talk. But there are several directions that we go from here. And on one side, you can start generalizing to other involutions. These are the simplest, and they deform nicely. And in fact, in a way that I might explain later, in some sense, sometimes it's convenient to study involutions by deformations, and so because these deform in the codimension 1 family, they're the first sort of loci to start with. But of course, the sort of the other direction is this sort of story of hyperkalers and Fanos, and so the questions, of course, are: is F the Fano always of K3 type? Meaning, does it have the cohomology of a somewhere maybe in middle cohomology, or not necessarily in middle cohomology, does it have some weight 2 Hodge structure that indicates that there is some relation with K3s and hyperkahler manifolds? And another question, of course, is does the derived category F contain K3 category in the same way that the cubic fourfold does? And of course, in the divisibility, of course, the remark here is in divisibility 2 and dimension 4, or n equals to 4, this recovers the example 1, of course. And so in dimension, the next dimension, so these questions, of course, are relevant when the divisibility is 2, because that's when you have the Fano component. And so in the divisibility 2, n has to be divisible by 4. So 4 is the first, and then we go to 8. So in dimension 8, so n equals to 8, we have a conjectural description of the cohomology of this Fano, or rather I say conjectural because we haven't written down all the details, but I think that we probably were not going to find surprises, hopefully. So it is indeed of K32 type, of the cohomology is 253, 22, and 1. This is the middle, and the rest is 0, the odd parts. Okay, so this is in dimension 8, and there's an analogous conjectural description of the derived category that I'm not going to rate because we're a little more unsure about that. And of course, then the next directions and speculations are, can you recover X as a moduli space of objects on this K3 category? I mean, this is completely speculative because for one thing, we need the derived category and we need bridge instabilities on it. So it's but sort of that's kind of the direction where these things are going. And maybe let me say one word about divisibility 1. The question there is it always the fixed locus of general type? And it looks like we can prove it in the next dimension. So the divisibility 1 case, the dimension 2 is K3s, dimension 4 are these WBW sextic, and the next dimension is 6. And in dimension 6, it looks like we can prove it. Again, it's not fully written down, but I think it should be okay. Okay, so I have 5 minutes, I think. So let me give you an idea of what goes into the proof. So the strategy is it's let me say, in the spirit of KLSV, which is Kolar-Laza Sacca-Rosen, you want to degenerate the pair X with the involution to concrete geometric examples. And what do I mean, concrete geometric examples? These will be moduli spaces of bridge unstable objects. On K3 surfaces. and then study fixed locus there. On these examples. And so there's some subtleties in this, because when you degenerate this pair, which is the same as disgenerating the pair of X with a line bundle, you lose the ampleness of the class. And so the issue is that the limit of the involution is not quite well behaved. And let me just end with an example that is just the example of K3 surfaces, which hopefully should convey how the degeneration of the involution is at the same a subtle problem, but also allows you, in fact, to prove the theorem. And if I might have need a couple minutes, the basic example of K3s is a family of K3s obtained by moving the curve. So with the sextic curve, and we take the double cover, and we assume that for t not equal to 0, this is smooth, and then for t equals 0, this is one nodal, has one node. And of course, then this gives a family of K3 over the disk, where either the central fiber is singular and it has an involution and it corresponding to the double cover of P2, or after a base change, you resolve the K3, but now the K3 surface is smooth and it's a resolution of that thing, but it still has an involution, but it's a wrong involution because it doesn't cover P2, it covers the blow up of P2. And so in this example, the fixed locus is a singular curve. In this example, the fixed locus is the normalization of the curve. And so this is exactly what we show, that we sort of construct things so that the same picture happens for hypercal manifolds, where you either degenerate to a singular hyperkahler with the regular involution where everything behaves nicely in families, but then of course the fixed locus will be singular, or you resolve after base change and you have an involution that is not of the same type from the lattice theoretic point of view as the one we're considering. The involutions from P1, the fixed locus, the invariant part of the action is just one-dimensional. And for this, it's two-dimensional because this has neuron severity too. So, so part of the sort of the strategy to prove is to first have a framework of studying the generation of these involutions, and then depending on what you want to prove, you pick and choose your degeneration so that the property that you want to choose is satisfied in the limit. And of course, you need an argument to deform back, because it's not just a nice, smooth family. All right, so my time is up, but I'll be happy to take questions and explain better.
Yeah, Giulia, I'm a little confused about this last example. So you're saying the branch divisor is has a node, right? Just has A1 singularity.
Yes.
So then the double cover also has just a node.
Yes.
A1 singularity. So it's on the interior of the moduli space. So this limit is unique somehow. So, right?
The singular one is unique. Yes.
Yeah, the singular one is also unique. It's in the period domain.
Yes.
There's a unique period. So how can you get two limits?
I'm not getting two limits.
But you're saying there is a second case when it's a double cover.
I'm just saying that it's a nodal thing. You can do semi-stable, you can base change and resolve the K3.
Right, and it's resolved just by inserting a single -2 curve.
Exactly.
Mm-hmm.
So what is your question?
But how can you get anything worse than just what's
So what I'm saying is just that the limit of the graphs of the involution degenerates to, in this, when I put a smooth fiber, to the graph of another involution plus stuff.
Oh, I see. Okay.
That's what I'm saying.
Mhm.
And so if I look at the family on the smooth model, the fixed loci don't work well. It's not proper over the base because I have to add the intersection of the diagonal with the other stuff. Does that answer your question?
I think so. Yeah, I think I got it. Yeah. All right.
Okay. Other questions? Maybe I have a question. Sorry, no, Marco, go ahead.
Go, Carlos.
Okay, so if you move the slides up a teeny bit, Giulia, just to the main theorem. I didn't quite understand, but from the example, I'm wondering whether I'm just not understanding. But are you saying that every K3 in that moduli space of hyperkahler, every X in that moduli space of hyperkahler manifolds has an involution? Or?
Yes, if lambda is ample, yes. And here, I think the general subpolarized. So
there's not a condition that that involution preserve the Hodge structure or some kind of thing like that.
Well, if the class is here, I'm assuming the lambda is an algebraic class. If lambda is an algebraic class, the reflection is a morphism, a Hodge structure.
Ah, I see. Okay.
So it comes with that. So the fact that the class is algebraic tells me that this is a integral Hodge isometry. The fact that lambda is ample tells me that there's an ample class, in particular Keller class, preserved. And so by the statement of polarized Torelli, there exists the thing.
Okay, but so are you? But do we expect that any component of moduli of hyperkahler manifolds has something like that happening? I mean, are there always involutions?
So for in the divisibility one case appears in all of the K3n types for any n.
But when you say, yeah, I guess I still completely understand. When you say it appears, or I mean, when you say that such a pair exists, but maybe that's my lack of knowledge about how these moduli spaces look. But I mean, there's one moduli space for each n, right?
Yes, there's one moduli. So for this deformation class, there is. And then within that deformation class, you may ask the question, which lattices appear as the Néron-Silveri of a family inside, right? It's the same as for K3s. And
you mean that you have to look at a subspace of the moduli space, which is ones that have that algebraic class lambda, basically.
Right. Yes.
I see. So there's a Brill-Noether locus.
Exactly. Yes.
I see. Okay. So there's like lots of, but so now I guess my question is, do you expect that if you don't fix the lambda in any component of the moduli of hyperkahler varieties, is there always going to be a non-empty Brill-Noether locus that's going to correspond to an involution like that?
So you mean independently of the deformation class?
Within your space of hyperkahler things.
Yes. So
is that Brill-Noether locus always going to be
non-empty? So I think if I understand your question, this is what this remark was doing. It was saying that these exist. So for any n, in the divisibility one case, and if and only if 4 divides n in the divisibility 2 case. Was that your question?
I think it is, but I guess what I'm sort of vaguely trying to wonder about is whether you guys would have as a kind of a long-term program. If I understand correctly, there's this question about, suppose you have a hyperkahler variety, is it always deformation equivalent to a K3 or a Grady or something like that? I mean, would there be a plan of like taking an arbitrary one and trying to look for one of these involutions and then get
in principle, but in practice, even if you say this is a lattice of a given hyperkahler deformation class, and say you even know from that lattice that there exists nice involutions, how do you study the fixed loci? It's not the reason why we win in this situation is that we can degenerate to these known examples. So
Right.
I don't know if this thing would go in that direction. It's more about extending this Fano hyperkahler relationship. I'm not ruling it out. And it's certainly an interesting thing to think about. I'm just saying that at the end of the day, you do need to study these fixed loci in some way, and how do you get your hands on them? We get our hands on them by looking at moduli spaces of objects on K3 surfaces, and there's a whole Macrì machinery there that allows you to study these things.
Okay, Marco, you had a question, I think.
Yeah, Giulia, do you have an explicit description of this Fano manifold, or just it is formal?
In genus 8, it's the limit is, so not really, and this is certainly one of the things that we plan to work on, and especially to relate it to these other Fano varieties that I've hinted at earlier. So let me just say that in the dimension 8 case, we know that these Fano manifolds degenerate to something that is some rational thing that is, we have an explicit series of birational maps that land in P8, and we're trying to understand a little better about what's going on. Of course, these birational geometries get complicated, but of course, the hope is to try to identify what are the things that come up. And I should say that if instead of saying square 2 and divisibility 1 or 2, we take other divisibilities, it should be the case that you get, for certain values that I don't remember now off the top of my head, you should get Gushou-Mukai 6-folds, if I remember correctly. So yes, that's certainly what where one heads to try to describe them.
I have a question. So like if the -1 eigenspace of the involution is not codimension 1, right? Then that just means that the Picard rank is higher.
And it deforms in codimension 2, yeah.
Or 3 or 4, depending on the size of the codimension of the -1 eigenspace. So like, do these results, do you expect them to apply in those cases as well?
I think so. I mean, depends what results, but I would say the techniques would. If
like the main theorem you have about the
I think that the precise statement about number of components, I mean, it would be a little too speculative now for me to say what I expect. What I do expect is that you use these techniques to study those examples, and this is what I was trying to say earlier. If you have this thing that deforms codimension 1, and then in the limit you have these other involutions that now have anti-invariant part of higher codimension, and so there's some kind of stratification going on where here at the boundary you have involutions where now the anti-invariant is dropping dimension, and so you kind of have some stratification thing going on where you may think of studying those involutions that you were saying as limits of these that you understand.
When you have all these techniques how to get from a Fano a hyperkahler, is it a priori clear that you only get K3 to the n type, or can you also get other things?
So you're talking in general when you have a moduli space of stable objects on a Kuznetsov component. Is that what you're asking?
Yeah.
Yeah. So okay, so the philosophy is if you have a K3 category, the deformation space works like the deformation of sheaves on a K3. So the X2 is the obstruction, and if the object is simple, then the obstruction vanish because X2 is one-dimensional, because in a K3 category, the X2 is surdual to the Hons. So, and so the work of many people, and certainly the sixth author paper, Bayer, Lautz, Macrì, Noor, Perry, Stellari, they certainly show that when these K3 categories are actually deformed to the derived category of K3, the moduli space deforms, and so what you do get is moduli space of objects on K3s. In fact, you also get O'Grady 10 type moduli spaces if the Mukai vector is not primitive, but it's of a Grady 10 type. So this is in the same, it's exactly what happens for K3s. And the same happens for Giulia Mukai fourfolds and sixfolds.
Can I ask another question?
Sure.
Sorry, but so when you're going from having the class lambda to getting the involution, are you using the Hodge conjecture in some way there?
No, just Torelli. Let me remind you what the statement is.
It's not going to be some kind of case. I mean, don't you get out of that?
I guess.
Well, lambda is a class in H2, right? So.
Yeah, lambda is a class in H2.
So we often know by that level.
And then from lambda you get this reflection.
But
that is.
But isn't some statement about the fact that reflection on the Hodge structure comes.
Yes. But
so you're saying that the Torelli theorem, the case of the Torelli theorem, which tells you that you have an isomorphism, that's sort of already doing.
Yeah.
Okay. Cool. Okay. Great. Thanks. So yeah. Are any other questions?
Well, thank you for your attention.
Yeah. So Giulia, thank you very much for a very interesting talk. So let's maybe thank Giulia. Speaker, please. Thank you. Yeah, so great. So thank you very much, everybody. So we reconvene tomorrow morning at 9 a.m. Miami time.